Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your dose of oil and gas intellectual stimulation by asking the technical questions. I'm your host, Yoga Shripradhan, and with me here today, I have Andrew McMurray from ShearFrac. Today, we're going to talk about SPE 200887, and I have the citation and the paper title below in the podcast description. I'm going to give a little bit of an introduction of Andrew before we start peppering him with questions. Andrew is a mechanical engineer with a passion for responsible hydrocarbon recovery and technology development. Throughout his career, Andrew has been successful in developing and executing disruptive completion technologies in the industry as an operator with Shell or as part of a service company, STEP. Before co-founding ShearFrac, Andrew was the general manager of Canada for Darcy Partners, focused on identifying, developing, and accelerating new technology across multiple petroleum verticals. Welcome to the podcast, Andrew.
Thanks for having me, Yoshi.
Well, I wanted to talk a little bit about ShearFrac before we get into the paper. So what does ShearFrac do for our listeners and viewers?
Yeah, ShearFrac is a technology company with hydraulic fracture guidance software and state-of-the-art reservoir engineering. So we make small adjustments in real time during the stimulation in order to improve fractured surface area and correlate that back to pressure transient and rate transient analysis in order to elevate operators' completions and help optimize fluid volume and fracture volume during the fracture operation, as well as discern well spacing and overall asset recovery.
Awesome. That's really good to hear. Well, I mentioned that we were going to go through paper 200887, which is identifying unique signatures of fall-off data during your completions. So could you walk me through that paper?
Absolutely. What we're doing at ShearFrac is calculating a fractured surface area during the active stage, and then we're looking at the post-stage fall-off information. So outside of the water hammer effects, we see the connection between the fracture network and the wellbore, assigning a fingerprint to the type of flow regime we see within that fracture network. From there, we can discern cluster efficiencies, fracture heights and half lengths, and learn on what changes need to be made to well construction or fluid and rate application in order to promote more types of linear flow regimes and higher ultimate recoveries as well.
Awesome. Thanks for that clarification. When I was reading through the paper, I think about typical PTA analysis, and really it's usually during opportunity shut-ins, especially for unconventionals. So I was just curious to know that when you do this post-stage analysis, what time frame is this flow regime identification you're doing applicable?
Right, that's a great question. We're looking at a very narrow window time of operation. I mean, this is during the stimulation, so we're trying not to slow the operations down. Normally, we put a pressure gauge below the master valve, allowing operators to change their wireline units and swab back into that well. So we're capturing around 15 to 30 minutes of that pressure transient signature, which doesn't allow us to have a very far depth of investigation, but it does give us a sense of how that frac is connected back to the wellbore, as I discussed.
Right, and I know that identifying that cluster efficiency and the uniformity of the frac, where others have used different types of diagnostics, such as the DAS, DTS, just to really identify how effective is your frac. And this is just another way to identify it. So that's really great. I also remember during the paper, just the different types of flow regimes. And one that really caught me was the spherical flow, or that negative half slope. And I know that negative half slope indication is usually limited fracture height. Could you also comment on other causes of spherical flow, such as even stress shadowing?
Absolutely. Yeah, you're correct there. I mean, within the analytical model that we build when doing PTA, we need to make some assumptions. And some things that go into that is obviously limited fracture height, cluster efficiencies, and then stress shadowing can be a big one. You know, we're seeing a lot of operators use more and more clusters, which we're seeing more and more types of spherical flow regimes. That tank is not extending as far as you can see with less clusters, where you're seeing higher fracture half lengths. The goal of ShearFrac is to try to create as much complexity within the same size of tank as you've historically done, which then promotes a more high permeability fractured network connected back to the wellbore.
Awesome. Yeah, I think about the different types of flow regimes, and I know we discussed this too. And when looking at the paper, I've seen that transition of different flow regimes too. And ideally we want to reach that linear flow, but there's that period of spherical flow where I always try to think about what that cause is.
Yeah, well, what we see is really interesting, actually, Yoshi, just a comment
Yeah.
on that is that from spherical flow, sometimes we see radial, and it depends on the time frame that we're looking at before it transitions to a bilinear or linear type of flow regime. So unfortunately, since we're just looking at a small, narrow snapshot in time, that depth of investigation is limited. But if you look at, consistent stages time after time, we're fairly confident that, when we look at our fractured surface area measurement during the operation to that leak-off surface area calculated during pressure transient analysis, those correlate or cumulatively correlate back to what we see in rate transient analysis, where after 90, 180 days of production, we see that further depth of investigation into the formation, and all those surface areas are lining up very nicely.
Awesome. Thanks for that clarification. I wanted to move on to just discussing different flow regimes and optimizing the fracture surface area. How can we have more control on what kind of flow regimes we like to see with the follow-up data? So if we're optimizing the fracture surface area real time, why are we doing this post-stage analysis to begin with?
That's a great question. We don't want to just make decisions based on one type of measurement. We'd like to have redundant information that come to the same sort of conclusion. Things like offset frac pressure transducers, pressure transient analysis, rate transient analysis, as well as what we can do within ShearFrac at this calculated fractured surface area, all lead us down the path to make a more educated decision. So there's small things that we can adjust, based on the wellbore construction, such as cluster design, your rate or fluid application, such as a working proppant concentration or a controlled breakdown to take advantage of the types of geologies that you're working with. All of these things can impact that type of flow regime. And what we're doing right now at ShearFrac is working with operators to understand how we can optimize this in real time, almost start manufacturing wells to, independent of the heterogeneity of the rock quality, try to match our hydraulic horsepower stresses with our rock stresses, which end up creating more fractured surface area and then better producing wells. And by doing this workflow that we've discussed, from fractured surface area to our pressure transient analysis surface area, we can identify how these wells are communicating almost in an interference test. There's actually a recent paper that we published at ERTEC discussing this exact same topic.
Awesome. Now I'll definitely look up that paper, put that in the citation in the podcast description, and I'll invite you again to pepper you with more questions too.
Thanks, Yoshi.
Yep. Well, I do a lot of RTA work, I've discussed with you so many times, and in our coffee chats and everything. How do we reconcile what we see in RTA for flow regime signatures versus this workflow? For instance, we like to see linear flow in RTA. And in this analysis, you mentioned that the linear flow means there's a predominant fracture. So how do we reconcile between this workflow and RTA?
Well, the interesting part of pressure transient analysis is we're looking at a smaller, narrow window in time, as well as a smaller stage. Additionally, we're looking at an incompressible fluid volume. So we don't have the same sort of uncertainties such as multi-phase flow effects, multi-stage flow effects as we do in RTA. We haven't yet had the chance to do this pressure transient analysis and then compare it back to fiber optics or a production log. However, we're very confident on the values that we're getting with respect to, A sub C root K in acres, where cumulatively our pressure transient values are lining up very well with that rate transient outcome.
I do want to point out though, and thanks for mentioning that, this came into my mind. I do want to mention that at ERTEC 3114, the paper that we wrote together with ShearFrac, we saw that correlation with that fracture surface area with our first order info when we preloaded that well. So it's great to see different diagnostics and converging to that similar conclusion. So thanks I'm really glad that you mentioned that RTA piece and how there is that there is that correlation with this workflow. There was one point in the paper that really sparked my simulation background, I would say, and it's meant for the shear or the complex fracture network equivalent to the dual porosity system. How can you make that kind of comparison to having a complex fracture network similar to that of the dual porosity system? Because with shear fractures, you're inducing those kinds of fractures.
Yeah, absolutely. I mean, there's a bunch of different scenarios you can do to model single porosity, dual porosity, triple porosity, or quad porosity. The way I like to think about this is dual porosity systems are looking at your matrix versus your fracture network porosity. Triple porosity systems would then include the differences between a tensile or shear type of failure. And then a quad porosity system would also include a natural fracture system. So when we compare what we do in the Wolfcamp to the Haynesville, for example, the Haynesville has low permeability porosity, but has high dual porosity system because of its natural fracture, because of the natural fractures existing within the substructure. Within the Wolfcamp, for example, we need these shear and tensile fractures because we don't have that same sort of natural fracture type of system. So by inducing more complexity in formations like the Wolfcamp, this dual porosity system is going to be much more prescriptive of how these wells are going to flow. I don't know, how you model different type of flow regimes within the software that you're working with, but what we're trying to do is constrain some of these assumptions that go into the models. So the more information that we can gather and the less assumptions we can make, I think the better your models are going to come out with better results.
Right. I personally haven't used any dual porosity system with any simulation. It just piqued my interest in terms of equating the complex fracture network with a dual porosity system, and wanted to know if there were any limitations to just using that dual porosity system. But thanks for really clarifying that and explaining the flexibility of the modeling. Well, I can't leave you without asking this question. This paper really piqued my interest, and I'm really passionate about RTA and PTA, and I'm pretty excited about the applications of this workflow personally. But I want to hear it from you in that what are some of the applications of this workflow that we haven't seen in the past in this industry?
That's a great question. Thanks for that. There's a lot of interest in interference testing at the moment. We're looking at offset pressure transducers, like we're seeing frac hits. How much of a frac hit is a good frac hit? And when you start to flow these wells back, we're starting to see production allocation issues across multiple laterals. When we look at the combination of fractured surface area measurement and this production surface area measurement, we can see if this production surface area is larger than our calculated fracture surface area, which could infer that we've connected to a depleted fracture network historically, or a new type of natural fracture network that is outside what we thought we'd created initially. And vice versa, if this fracture network is looking much bigger than our leak-off production network, this could infer that we have some sort of near wellbore tortuosity, stress shadowing, or additional stress effects that are preventing our ability to see that new fracture network connected back to the wellbore. And that is discussed in this ERTEC paper that I will provide reference to at the end of this podcast.
Awesome. Well, Andrew, it was really a pleasure having you in this podcast. I'm glad that you let me pepper you with questions, and it piqued my curiosity, and I cannot wait to hear more of the results that your organization is doing with this kind of workflow. I'm really looking forward to more examples and even seeing the corroborated results with other diagnostics.
Yeah, well, I've really got to thank Dr. Mazhar Hassan, Ahmed Ibrahim, Tom Johnston, and Wes Johnson for writing this paper. I'm not named on the paper, but I hope I did it justice. So thanks, guys, for the support.
Awesome. Well, listeners and viewers, you heard it from Andrew. Please be sure to check out the paper 200887, which again, I'll mention the citation in the podcast description and in the YouTube video. Please be sure to leave me any feedback or any other papers you wish for me to review. And once again, I'm Yoshi Pradhan, and I'm signing off.